to the right. So you have a current carrying wire directed to the right. And you want to find the magnetic field at point P, right? You want to find the magnetic field for a small section of the wire. I noticed there's two typos on A and B. I want you to find the field due to a small element. So we were really trying to find dB. We want the expression for dB at point P at location X. So which one of those expressions is the correct dB? Notice in A and B that there should be a D in front of the B. I messed those up. So those aren't B's; those should be dBs. Okay, and in fact, I will change them as you're looking at the question, or I'll try to change them. Actually, I'll wait till we're done. I'll wait till we're done. Just go ahead and answer the question. And as you do that, I'm going to set up this problem on the board as you're trying to answer this question. Okay, so I just need one more person to respond. Okay, so everyone has responded, and I have, of course, I do have a distribution of responses. So let's go over it real quick. So actually, let's take a look at the results. You guys see the results? Let me stop sharing. And let's try this. So let me change the screen settings, sorry. This is a Biot-Savart problem, so I need to figure out my ds. Well, my current is going to the right, so my ds is just going to be I hat dx. Okay. My r hat is this vector, and this is the angle theta. Then my r hat is going to be cosine theta I hat plus sine theta j hat. My r squared is just r squared. So I'm just going to write it like this. Then my ds cross r or I'm sorry, ds cross r hat, I take the cross product of these two, I get 0. I take the cross product of these two, I get something in the k hat direction. So I'm going to get sine of theta dx in the k hat direction. So then I put this all together, dB, and the question is asking for the magnitude, but we'll get to that, is mu 0 over 4 pi times I ds cross r. I'm sorry, ds cross r over r squared. So all I got to do now is figure out what sine of theta is. Sine of theta is basically going to be this distance divided by the hypotenuse. And so that's going to be r over, big R over little r. And so dB is mu naught I over 4 pi times r over r cubed, and I forgot my dx, didn't I? So that's the magnitude of dB. This term in brackets is the magnitude of dB. So the answer to that one was B. You folks okay with that? Okay. Next question is an Ampere's law question. So you have an Amperian loop. It's a complicated Amperian loop drawn around two wires carrying I1 and I2. The loop is irregular and folded over between two currents as shown by the arrows. The wires are inclined at the angles theta 1 and theta 2 to the plane of the loop. What is the value of the integral of B dot ds as shown around the loop? So let me relaunch the poll. Okay, so everyone's responded. So let me end the poll. And this was a little bit of a harder question. Okay, so we have a distribution of answers. So let me stop sharing. Let me write down Ampere's law. So Ampere's law is this: the integral of the magnetic field around a loop is equal to mu naught times I enclosed. If you integrate the magnetic field in the same when you integrate the magnetic field and dl are in the same direction, then this integral is going to be positive. If they're in opposite direction, they're going to be negative. So when you look at the two loops, you're going to end up with one positive, one negative value, because when you think of the sense of the current and the magnetic field. Now, when you look on this side, are there any angles here? Hold on a second. Yeah, we'll get to that, Patrick. Hold on a second. I just opened up something that I didn't want to open. Okay. You're on the right track, Patrick. There's no angle here, right? There's no angle dependence. It just depends on what penetrates the loop, regardless of the angle. So if you have a loop of wire, and let me get some, not a loop of wire, I'm sorry. I just have an Amperian loop, and let's pretend this is carrying current. No matter how the current's going through my Amperian loop, you got to count that as the I in the wire, okay? So that eliminates essentially all of them except E and F. But when you look at I1's coming towards us. Okay, when you look at I1 coming towards us, the magnetic field is opposite to the direction of the way you're integrating. So that's going to introduce a minus sign. When you look at I2, you're integrating in the direction of the magnetic field, so that dot product is positive. And as a result, you're going to have this as what's enclosed. Even though the currents are in the same direction, the direction of the integration are in opposite directions. So that's going to introduce a minus sign. If you look at it, the magnetic field due to I1 is counterclockwise as we're looking towards the screen, whereas you're integrating clockwise. That's going to make this dot product -1, and that's going to introduce the minus sign. Whereas in the second case, both the magnetic field and the Amperian loop are counterclockwise. And so when you take the dot product between those two, that's going to give you a 1. Are we okay with that? Okay. One more question. So I have a solenoid carrying current I, and this should be straightforward. What is the direction of the magnetic field inside the solenoid? Okay, everybody's answered. That was pretty quick. Okay, let me end the poll. Let me share the results. So we have two answers that people have chosen. Well, there's only 4 folks in here. Okay, let me stop sharing. So all you got to do is use the right-hand rule. And what I would do, I look at the one on the right. I'm sorry, the one on the left. All I have to do is look at the current coming in on the left. My thumb points in the direction of the current. My fingers curl around the magnetic field. Okay? And so when you look at inside the loop, when I curl my fingers inside the loop, my fingers are going to be moving my fingers are going to be pointed to the left inside the loop. And so the field is going to point to the left. So the answer is 3. Are we okay with that? Okay. All right, so what questions do you have on the homework assignment? Any questions on the homework assignment? Okay, because it's due Friday. No questions? And I did talk about the more difficult one in class today, the last problem. So I kind of got you started on the last homework problem. Let me change the view. You do have 16 problems, so they're actually not that long, these problems, but except for the last one. Another difficult one. So I should say something about number 15. And it's not difficult, but it's tricky. For part B. In part A, you have to assume that one of the wires is infinite. But in part B, since the rod starts at the left end, you know the end of the wire, you got to think of it as the rails being semi-infinitely long. In other words, if you remember when we applied the Biot-Savart law to calculate the magnetic field due to the wire, and we made it infinitely long, I had something like this. I hope I remember this right. Okay, when I made this infinitely long, this angle was 0 and this angle was 100, this angle was 180 or pi and this angle was 0. And so this ended up being mu sub naught I over 4 pi d, 2 pi d, sorry. But in this particular problem for part B, because you know you're at an end, right? Because you're starting at one end, you're starting, let's say, at this point, and then this goes to infinity. Instead of this being 0, this is pi over 2. So you have a semi-infinitely long wire. Does that make sense? So that's something tricky about that one, is that because the rod starts at an end, because if it was infinitely long, you couldn't start it at an end, right? So you'd be integrating from pi over 2 to pi. And so you would end up getting half the field of the fully infinitely long wire. So that's one tricky thing. In fact, I did. This one I essentially did in class, so this shouldn't be hard. I talked about like something like this in class. These are not very difficult. Like 12, don't confuse diameter and radius. I just don't see something super tricky anywhere in here. I think 16 is the trickiest one. Of course, if you look in the book, it's a red-coded problem. How would the currents be distributed in equation for number 9? Let's look at number 9. Yeah, I have to blow that picture up because it's really hard to see the arrows. When you look at I2 goes into the plane, I1 and I3 come out of the plane. Okay? So you just want the magnitude of the field. So I1 and I3 add, and then you subtract I2. That's the current. Okay? Yeah, just that I3 is, I2 you would consider negative. Yeah, it's hard. I mean, you have to magnify it. If I looked at my printout, there was no way I'd see it. Okay? Yeah, so you do have to magnify it. It's not the greatest picture. So I think you can see there that I2 is in the opposite direction. So that's an Ampere's law problem. I did find, between classes, I was finding looking for a video on Ampere's law. I found a great description in a solenoid, the application of Ampere's law to a solenoid online, and so I'm going to give you that link. Typically, in a textbook and when we lecture, we don't really give a full treatment of the solenoid using Ampere's law, but this person does, and so I'm going to send you the link to that one. He does other stuff too, but there's a nice treatment of the solenoid, so I'll send you that. Give you another example of Ampere's law. He actually goes through and proves that the field inside the solenoid is uniform using Ampere's law. Whereas typically we just do it by intuition. Any other questions? On number 5, just realize that the direction of the current in the circular parts is in the same direction as the magnetic field, or in the opposite direction of the magnetic field due to I1. And with number 4, just be careful with algebra, with making silly errors, because I did that. Okay. And I think doing number 4 will help you to do part B in number 16. And this one I did in class. The rest of them are pretty straightforward. There's nothing hard. Although what I would do if I were you when you do this problem, number 1, you really need to just start from scratch, apply Biot-Savart law and do it. Okay, don't just plug numbers into an equation, because that's not going to help you practice for the exam. Because on the exam, you're not going to be plugging numbers into an equation. You're going to be using the Biot-Savart law to derive the equations, and then you're going to plug in numbers. So to do number one, you really should go through Biot-Savart law. The more practice you get, the better it is for you. And you kind of know what the answer should be anyway. Because I did the case where I did one of these sections. Okay. So you folks don't have any other questions? I mean, I will have office hours tomorrow. I guess I'll check Discord. And Patrick, you had a question. So I'll probably have to send an email to everybody. But Patrick, you had a question about the electric motor. And regarding me hooking up the electric motor, the demo I showed in lab, hooking up in series and parallel. So right after my second lab, I hooked it up I hooked up the motor in series, and it ran at 6 volts. So then I measured the resistance of the armature and the resistance of the electromagnet. The armature's resistance was about 2.1 ohms, and the electromagnet was 0.8 ohms. So that was about a factor of 3. Okay. But that doesn't account for the fact that the current is not even doubled. And the reason why that is because the magnetic field is not only created by the current, but it's also be created by the iron that goes through those loops. And when you magnetize iron, its magnetization is not linearly dependent on the current. Okay. And granted, we have not talked about magnetization, and we don't have time in this course. Magnetization is somewhat complicated, and you really don't get linear expressions for the relationship between the magnetic field and the current. But it's because of the fact that you have an iron core inside. I think if we did it without an iron core, you would probably be correct in assuming that, if you double the resistance, then you'd have to double the current. In other words, if you go from series to parallel, if you double the resistance, you would double the current. In this case, I tripled the resistance. I should be able to, double the voltage. If I triple the resistance, I have to triple the voltage. But because of the fact that the iron gets magnetized, that linear relationship is gone. Okay, and it's really, a lot of it's just due to the magnetization of the iron, which is quite complicated. And unfortunately, we don't have time to talk about it in the class. But if you took a junior level class, either in engineering or in physics, you would learn a little bit more about it. So anyway, I'll send an email about that. Any other questions then? Okay, so I'm going to end it here. You folks have a good weekend. Or maybe I'll talk to some of you tomorrow. All right, take care. You're welcome. See you next week.